All right. This is another piecewise defined function. It's got three pieces. You need to graph each of these pieces, but you have to do it with the appropriate cutoffs. Now we should understand what each of these look like. If I cover up these bottom two, what does that first function look like? It's an absolute value shape. What is the second guy? Parabola. Quickly, what else do you know about it? It's upside down, shifted up 6. What is this guy here, the bottom? It's a constant function. It's just a horizontal line. So here's what you're going to do, piece by piece. We're going to break this guy down. If I were to look at this, f of x equals the absolute value of x plus 5 plus 2. You said it's a V shape. What else do you know? Left 5 up 2. Pay attention to your demarcation up here, which is less than or equal to -2. So that means this guy will only go as far as -2. So let me get that on here. So where's my vertex for this absolute value function? -5, +2. So am I stretching this guy, opening upside down or anything? No, so normal slope. Now what kind of point will it have when it hits that green cut line? Less than or equal to, so it will be round and closed. So let's make it happen, Captain. So up 1, over 1. It's going to be closed right there. I'm going to stop. Don't go any further. What? Oh, if they said something going down, I'm like, what? Notice that when I get to this endpoint, I stop. There is no arrow. But going out to the other side, I do have an arrow because he does go on forever in that direction. The conditional statement here said that you're going to look like this guy when x's were less than or equal to -2. So less than -2 is on the left side here, which is why I have that V shape right there. Okay. Now, the second guy that we had was basically -x² plus 6. You said this guy was a parabola. What else do you know about it?
Upside down, shifted up 6.
Up 6 and upside down. Okay. But notice the conditions that you have for the squaring function. Your x's that you're using are between what?
-2 and +3.
-2 and +3. So that means your cut lines are at -2 and +3. So what section are you going to see your parabola? Right in between those guys, right? Because you're cutting it off. You say, hey, parabola, here you are. And the parabola's like, yay, I'm a parabola! Oh, wait a minute, I'm sorry. I got to cut you off at -2 and at +3. So now it looks like Venus de Milo, right? The statue without the arms? Yeah.
Yeah.
Someone needs to take art appreciation.
Talking about the Nike.
Just saying.
Just saying. I did take it.
Nike, Nike, Greek word for what? Victory. So that means I start up 6. It's a parabola opening upside down. What's 1 squared? What's 2 squared? And 3 squared is? Now, do I get to be equal here at the cut line or not? Open circle. Go the other way. -1 squared is 1. -2 squared is 4. Open or closed? Open, because if you look at my inequalities here, neither one of them were equal to. So now we graph the parabola. So given those cuts that I made, that's exactly what my parabola looks like. What about the last guy? Constant functions are nice. What was that?
So this is crazy.
Crazy fun. Here, what does 4 look like? If I just were to write y equals 4, what does that mean?
Horizontal line of 4.
Horizontal line going through 4. Do I draw this all the way across?
Starting at the x 3.
Open or closed?
Start at 3, 4.
It's closed.
That would be a ray. So that by definition is a ray, correct?
This section right here is a ray. Endpoint going off forever in one direction, straight.
It's an array. Is it a ray if it's a closed open circle?
It's technically not.
I thought it had to be a closed.
Yeah. So what's the domain for this?
Negative infinity to infinity.
Domain is all real numbers. So if the domain is all real numbers, will the function ever be undefined? No. If it's all real numbers, that means you can plug in anything you want to. What is your range?
Negative 3 to infinity.
Negative infinity?
Negative
Where's this guy going all the way down?
Negative 3 to infinity.
Don't raise your voice at me. It is from negative 3 to infinity. This guy right here goes from negative 3 up to 6, but this guy would continue going on up forever, so you would get to include everything beyond that.
Sweet.
Now, why is that important? No.
Like we showed earlier, piecewise-defined functions are used.
Okay, so how's that going to help me at the restaurant? I mean, I understand figuring out the equation, but why is it important to be able to graph it? The graphing side of it.
At a restaurant or changing a diaper, piecewise-defined functions probably aren't going to help you a whole lot. However, depending on the field that you're going into, you need to be able to understand how shapes will change based on the criteria and based on what the input values are. And so we're working with is an example of how a piecewise-defined function works. This exact example may not be used later, but it is the building block for bigger and better things. Now, if I ask you to evaluate f of 0, I've got 3 pieces here. Who takes 0?
6.
Is 0 less than or equal to negative 2? Is 0 between negative 2 and 3? Then it goes there. Plug in 0, what do you get? 6. Notice how in the graph, you actually have this point right here. 0, 6.
0 plus 5 plus 2, I thought was 7.
But I had to plug it in here
Oh, over on the second one.
0 is not less than negative.
because 0 doesn't satisfy this original condition of being less than or equal to negative 2. Just like if I would go into CC's and I say, I want the kids buffet. I don't satisfy the conditions for that, so it doesn't apply to me. If I ask you to evaluate f of negative 6, is negative 6 less than or equal to negative 2?
Yes.
So plug in negative 6. What do you get? Absolute value of negative 1 plus 2 gives you 3. Look over here. Right here is the order pair negative 6, positive 3. What is f of 3? Who takes the value of 3? Is 3 less than or equal to negative 2? No. Is 3 between negative 2 and 3? No. Is 3 greater than or equal to 3? Yes. So you plug in 3 here, what do you get? You get 4. And you see, you actually have this point here when x is 3, y is 4. You check, and we have the same thing.